Alright, hi everyone. So this will hopefully be our one lesson of remote learning for physics, and hopefully we will be back on Wednesday. I'm recording this on the Friday, so I don't know, you'll probably know better than me watching this. I've decided to, if you look at the timeline, the question plan, you'll see that we've got two lessons left. One's from 9.2 and one's from 9.3. I've decided to flip those for this lesson. This one's going to be better to do remotely, and the 9.2 one is better to do in person because I've got some stuff to show as well as the PowerPoint. So what we're going to do is just flip those around. So if you look at your question plan, we're looking at lesson number 8 on chapter 9.3, not lesson number 7 on chapter 9.2. So don't get those mixed up. We're looking at 9.3 today, and then we'll go back tomorrow, hopefully on Wednesday, and do the next part, our final part of this topic. So the plan is to do that, then spend a lesson on revision, and then the test will probably be next Tuesday. So hopefully things work out that way. If not, we're going to have to adapt, but that seems to be the plan at the moment. So test next Tuesday, assuming everything else goes right. So we're looking at electromagnetic waves today. Should be a pretty straightforward lesson. Hopefully this will run all right. So as we've covered before, for a long time there was a debate as to whether light was a particle or a wave. This chapter is called Light as a Wave. It examines the characteristics of light that are wave-like. The next area of study will examine the characteristics of light that are particle-like. Now, when we consider light as being a wave, we say that light consists of electric and magnetic fields, which are both oscillating perpendicular to the direction of the light's movement. And that is what's being shown in that picture there. You can see you've got two waves, the red one and the blue one. The red one's the electric field, the blue one's the magnetic field. You can see that as the light travels to the right along the arrow, the electric and magnetic fields that make up light are getting stronger or getting weaker, changing direction. They're oscillating in strength and direction. You can see the wavelength of the light is between the two peaks of the red wave, or it could be between the two peaks of the blue wave. This is how we visualize light as being a wave. What a wave of light is actually going to look like is what's shown there. Now, since light is a wave, we can describe it with the wave equation. We did this back in chapter 8. We said the speed of a wave is equal to its frequency times its wavelength. However, since we know that the speed of light in a vacuum is always c equals 3 times 10 to the 8 meters per second, this equation can be written where we replace the v with c, the speed of light, because that's how fast light is moving, and that's our wave equation for light. C equals f lambda. We use that quite a bit when we're talking about light. So a basic example would be, what would the frequency of light be if its wavelength was 500 nanometers? So we grab our wave equation for light. I've rearranged it, so now I've got f as the variable that's on its own. So frequency is speed of light divided by wavelength. I plug in my numbers. The speed of light in the vacuum is 3 times 10 to the 8 meters per second. The wavelength of the light is 500 times 10 to the negative 9. Remember, we've got nanometers. Our numbers lengths always have to be in meters, so we convert our nanometers into meters when we do our division, and that gets us out 6 times 10 to the 14 hertz. Remembering that frequency, it's got units of hertz. That's just something we've got to include in our answer. Now the next part is really just going through the full electromagnetic spectrum, looking at all the different kinds of light that we have, and this is a nice colorful PowerPoint, so hopefully it works out alright. So we've got radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. We classify light into one of those depending on its wavelength or its frequency. We've got visible light sitting kind of in the middle. There are some that come before visible light in terms of frequency, some that come after it in a higher frequency, and we're just going to work our way through those and get a handle on what exactly they are, what they do. And you can see some pictures down there, buildings, humans, honeybees, things that are about the same size as certain waves, just to give you a point of perspective. So we start with the biggest of waves, which are the radio waves. They can be about a meter in length or thousands of meters long. We use them for things like telecommunications, TVs, radios. Obviously, they're called radio waves. Because they're so big, they're very safe. They're the safest of waves just because they are so large. Frequencies, the numbers there seem kind of big, but in terms of the frequencies for light, those are actually comparatively small. So we're going to see much higher frequencies for the waves than that. Even if those numbers do seem big, it's not big in the scheme of things. Now we've got microwaves, which are the smallest one, the next biggest one. Sorry, I'm getting this back. After radio waves, they're the next largest one. So even though they're called microwaves and micro sounds like really small, they're actually pretty big in the scheme of things compared to the other kinds of light. We use microwaves in surprise microwave ovens. We use them for things like radar, and we use them for telecommunications as well. Dangers: they can produce burns and they can produce cataracts, and some people think they produce cancer. I'm not sure, but I probably should take that out of the PowerPoint, but whatever. Basically, there's the second kind of waves, and like all the others, we're going to make use of them in certain ways. You can see the wavelengths, you can see the frequencies there. We've got infrared, and infrared is basically the light that goes with heat. If something is giving off heat like a flame, it's basically going to be emitting infrared radiations. So things like night vision goggles can pick up on the infrared light given off by objects that are emitting heat, and that's how infrared goggles, night vision goggles, can detect things in the dark, because they're detecting the heat, the infrared given off by the objects. Using things in TV remotes, heating, cooking. Dangers: they can burn as well, because hot things can burn you. You can see the wavelengths there, getting down into the nanometers, which is where a lot of light tends to sit. Visible light, it's the stuff you see, red, blue, green, etc. You've got a typical range for wavelengths in like the hundreds of nanometers, so that's just kind of a useful thing to know. You've got at your low end for wavelength, you've got your violet light at about mid 300s up to about the mid 700s for red. It can be beneficial to just have a rough idea that visible light is going to be sitting somewhere in that range, and you use it to see things. It's visible light, could have even skipped this slide. Then we get into the ones that are lower wavelength or higher frequency. So it's going to depend on which way you want to look at it. You've got ultraviolet, UV radiation, the stuff that we get told, avoid it from the sun, etc. You can see that it gets used in a few different applications, but mostly people try and keep their distance from it because it starts getting a bit dangerous. You can see one of the dangers is skin cancer. You can use it in things like tanning salons, discos, detecting counterfeits. Bees can detect it, so that's, bees are awesome. Fun bee fact for you, but that's basically it for ultraviolet. X-rays are used in X-rays, in medical imaging and in security. When you go through airport security, they use X-rays to see into your bags, your suitcases and whatnot. It can cause cancer, so when you get an X-ray, the radiation specialist needs to stand behind the thing so they're not exposed to it. You can only have so many X-rays a year, because they can cause problems, cancer. You want to avoid exposure to them. I'm going to go through that a bit later in the later slide. You can see the wavelengths are getting very small, below 10 to the 12s below the nano. It's down into the picometers. Frequencies are getting very high, up to the 10 to the 20s. So those are getting big. And then we got the final one in terms of wavelengths and frequencies. So wavelengths are down to the very small, frequencies are up to the very high. Gamma rays are a bit of a double-edged sword. They cause cancer in this, if you're exposed to it. They're also used in cancer treatment because they're very good at killing things, and so they can be used to do things like kind of try and cut out tumors, but it's a bit of a two-edged sword, like I said, because you use gamma rays to try and cure cancer at the same time it causes cancer. What are you going to do? But that's basically the last one that we're going to be looking at. The other slide is just talking about the dangers of them. We talk about some kinds of radiation, ultraviolet, X-ray, gamma rays, the high frequency, low wavelength ones as being what we call ionizing radiation. Eventually the waves get so small that they can interact with cells, DNA and atoms, and that's the point at which the radiation is going to start causing damage to cells, because they've got so much energy, because their frequencies are so high and their wavelengths are so small. So that's just the final thing about these kinds of radiation, just being able to kind of recognize that some of them are pretty safe, and some of them are considered more dangerous, although of course microwave radiation and infrared radiation can still cause harm just not as easily as the other three kinds on the high frequency end. So that's basically all this lesson is. You just need to be looking at your checkpoints textbook questions first from chapter 9.3, then answering the checkpoints questions. This should hopefully be a pretty quick one, and then hopefully you'll be back tomorrow so that we can do 9.2 and get this topic finished. And that is it from me.